Okay, good afternoon, everybody. We are very happy to have here Professor Philippe Grandier as our speaker today. Thank you very much for accepting our invitation to visit our institute and give this seminar, very special seminar. Let me present him. He did his thesis under the supervision of Professor Alain Aspect and participating in Alain Aspect experiments, resolving the EPR paradox. He's co-author with Alain Aspect of 2 papers related to this experiment. Philippe is research director at the CNRS, head of the quantum optics group at the Charles Fabry Laboratory in the Institute of Optique in Orsay. He is also professor at the École Polytechnique. He did a lot of work on the quantum properties of light, such as experimental realization of compressed states, single photon states, and non-destructive quantum measurements. He is currently pursuing research in the field of quantum information and quantum cryptography, in particular using microscopic optical traps to manipulate individual atoms. He has been the coordinator of several large European projects related to the quantum optics and quantum information processing, including scalable quantum computing with light and atoms integrated project. His achievements has been recognized by national and international awards. Today, we will discuss a little bit about his Ph.D. project under the supervision of Professor Alain Aspect. And thank you very much again, Philippe. And just to, this seminar will be transmitted via YouTube, as was announced by the SBF organization. Thank you very much.
So thank you for the kind introduction, and it's a pleasure to be there. Thank you to Vanderlei also for the invitation. I had a little trip in South America, and I thought I could not miss San Carlos. So it went well. Okay, so I will speak about sort of a little bit of historical things that I did many years ago with Alain Aspect. So we did a series of experiments in Institut Optique. So now Alain just got the Nobel Prize. For part of this experiment. I will give more details later. But it will be about Bell's inequalities, but not only Bell's inequalities, because actually we did many other things, especially about single photon and single photon interferences. Okay, so it was all that was done in Institut Optique. So it used to be this building in Palaiseau, in Orsay, sorry. Orsay is here, so you see it's Paris. It's about 25 kilometers from Paris. There is a train line here. And this is the whole building where all the experiments I described have been done. But since then, we have moved. We are now in Palaiseau. No. Here. So Palaiseau is just a few kilometers away from Orsay. So we have a brand new building, which is called now Institut Optique Graduate School. So it's English, but we are in France. But you know, to be fashionable, our director decided that we will be a graduate school. It's an engineering school also, where we have many students. And so the experiment I will describe have been done here. So we still have this building. We are thinking about changing it into a museum now. Okay, so it will be about quantum physics. So you know, quantum physics was elaborated at the end of the 1920s by big names, Schrödinger, Heisenberg, Dirac, Born, etc. I like to tell to my students that it's a good candidate to the title of greatest intellectual adventure of the 20th century. I mean, greater than relativity or than psychoanalysis, for instance. It's really an important thing. It's a theory at the basis of our understanding of the physical world. It explains stability and structure of matter. You know that matter is unstable. Without quantum mechanics, the electrons should fall on the nuclei. They don't, because they are quantum. Also, what is light? I will speak a lot about that. The interaction between matter and light. So this is really a fantastic theory. Perfectly coherent formalism, huge success, incredible number of applications, transistor, electronics, telecommunication, medicine, nuclear magnetic resonance, and all these things. So it looks super nice, but there is a but. It keeps a mysterious character. That is, it's a non-deterministic theory. Probabilities are absolutely essential. It's non-local in a subtle way. I will come back to that also. And there is no simple correspondence between quantum objects, the atoms, and the macroscopic world. And you know the stories about Schrödinger's cat, etc., which play with this kind of difficulties. So what I will try to do is to illustrate, that is, yes, and another point is that since about 40 years, we have what is called the second quantum revolution. So the first quantum revolution started in the 1920s. It gave us a lot of things, lasers, transistors, but it deals about many quantum objects. Now, if you go down to the single quantum object regime, there is a really nice collection of new things. I will speak about that, linear superposition, entanglement. And these new ideas turn out to be very useful. I will also give example. So I will mostly speak about light, photons, introduced by Einstein. So this second revolution, you know, this name was sort of introduced, I'm not sure, by Alain Aspect himself in a French book. And so now it's a very useful concept to say that we are attending a transition between the first and second quantum revolution because we just access individual quantum objects. So the light wave of a particle, one photon is strange, two photons is even stranger, and I will discuss all that. So if I want to be a little bit historical, the basic question is light made of a wave of particles? So, oops, yes. It's a super old question. You know, the Egyptians already had an idea on that. You see, it was simple. Light was flowers. And you see Princess Taperet taking a sun bath because the god of sun, Ra, sent her flowers. This is quite a funny theory. But so if we go a little bit in the scientific age, the fight begins. Because in the 17th century, there were already two opposite theories. The French Descartes was for particles, and the Dutch guy, Huygens, was in favor of waves. So, okay, they did not really agree. And then the next century came Newton. So Newton was you know, super Newton, and he decided that light are particles. And it was for some 1 century the end of the story because the power of intellectual power of Newton was so high that nobody could oppose. But okay, no, after the death of Newton, well, it started again. And in the 19th century, waves were back. And Thomas Young for experiments, Augustin Fresnel for theory in France, made a theory that is explained interference, diffraction, all these things, with a wave theory of light. And it's really culminating in Maxwell's theory. At the end of the 19th century, we had Maxwell equations, which are a super monument. So it was clearly decided light is a wave. But no, not yet. Just a few years later, beginning of the 20th century, photon, a particle of light, came again with Planck and Einstein. So this idea of photon was extremely difficult to swallow by physicists because just Maxwell theory was working so good. So Millikan made a lot of experiments. The paper, Einstein paper, it was in 1905. And then during 10 years, Millikan did experiments and wanted to prove Einstein wrong. But after 10 years of effort, you see, I was compelled to answer the unambiguous experimental verification in spite of this unreasonableness of the photon hypothesis by Einstein. So he doesn't look very happy, but still he got the Nobel Prize in 2030, and Einstein also in 21 for the photon, not for relativity. Okay, so at the end of the 1920s, it was more or less admitted that all microphysics entities, photon, electrons, there was De Broglie also, Davison and Germer, etc., have complementary wave particles duality. So the only possible description was quantum physics. But, not ended yet. Erwin Schrödinger, who is really one of the founders, wrote in 1992, we never experiment with a single electron or atoms or photons or molecules. This invariably entails ridiculous consequences. I think he even wrote, it would be as crazy as resurrecting a pterodactyl, you know, these prehistoric birds. And it was much before Jurassic Park. But you see, it was something, he was really unable to understand quantum mechanics elsewhere, in another way than a statistical theory. And so when you go to the single entity regime, you have some problems. So this would be Schrödinger's nightmare. It's a photon gun. Each time I click, I get one photon. Click. So this is one photon. So it's a photon gun, perfect single photon source. So it would be just incredible for Schrödinger, but no, this is done every day in the lab now. And so how to do it? So the idea is simple, well, sort of. That is a lamp like that emits 10 to the 20 photons per second, it's too much. How to get only one? So you can dim the light, but you don't know exactly where to go. There is a better trick if you believe a little bit in quantum mechanics. You excite a single atom, and then just from energy conservation, you get the energy of the single photon. So if you are able to excite one atom, you will get one photon, and if you excite atoms one per one, you will get photons one per one. And this is actually easy to do. You can do that just under a microscope. You put a little piece of diamond, and in diamonds there are so-called NV centers, which are actually nitrogen molecules coupled with vacancy, and they behave like a fixed molecule inside the diamond crystal. So you just need a little piece of diamond, you excite with a laser pulse, for instance, and you will get single photon one at a time. It's a simple experiment once you go the trick. So this is a little bit more about diamond. So you see you can get these little defects in bulk diamond, also in little diamonds crystal, nanocrystals. So the thing absorbs in the green, emits in the red, and you can get photon one per one. So this is a well-known idea. This is now an experiment for students. But okay, we did that 20 years ago already, many others did. So you see you have a microscope objective, a little piece of diamond. You send a laser beam here. You can scan your laser on the diamond to look for the little bright spot, and you see something like that. When you have that, this is actually a single atom and single NV centers. And this single NV center is expected to emit photon one per one. So if you send laser pulses, you collect the red light now, you split it on the Möbius splitter, you put two detectors, and if photons come really one per one, there is an effect called anti-bunching. After detecting a photon, it takes some time to detect another one. So a little bit more detail. So if you have, for instance, pulse train, so this is a pulses of light. First, you may assume that light is maybe either classical or maybe quantum if you have one photon per pulse. Then you split the light, it goes through two detectors. So if it is classical attenuated pulse, there may be two detections because there may be two photons in the same pulse. Whereas if it is a real single photon pulse, there is no double detection, and within a pulse, you will get only one click. That is, we never get any double click. So what I plot here is the number of double clicks as a function of the delay. So you see here it's 2 clicks within one pulse. You see it's a click between the first pulse and the next pulse, and the next pulse, etc. So you have pairs of photons everywhere, all over the place, because it's just attenuated laser. Now, if you have a real photon source, what do you expect? Well, you expect that this peak should vanish, because there is only one photon per pulse. And if you put a little piece of diamond, this is indeed what you get. You see there, the poles are broader due to the lifetime effect, but the vanishing of the central peak tells you that you emit photons one per one. So we did many variants. I did an experiment like that in my PhD thesis. This is a more recent one that we did with some colleagues. So you see the single photon emitter, basically. And then you have these single photon pulses, and you use what is called a Fresnel biprism. You split the beam like that, and there is an overlap region here. You can see you can expect some fringes, but first you send them to two detectors. And then if there is only one photon at the per pulse, only one of these detectors should click at a time. And this is what you see indeed. There is almost no, always little defects, almost no pairs double detection at zero delay, but you have separated pairs of photons, and this basically demonstrates that you have one photon at a time, one photon per pulse. Now, what happens here? If you have only one photon, it should go either here or there. But if it goes either here or there, you cannot get interferences. Well, so you look, and this is what. So you have now photon coming one per one, and this is what happened. So you see, this is a screen now, this is a camera, and you see little dots appearing, and the little dots sort of arrange, and you do see fringes, but it's really fringes with photons coming one per one. So this experiment was done in École Normale Supérieure de Cachan, where Alain and myself did our studies with some young colleagues. You will see pictures later. So it's really a pulse excitation. We produce a train of single pulses, and this is a clear illustration of wave-particle duality. We are now sure that photons come one per one, but still we get interference physics. Okay, so this is the physics. After that, you can say many other things. Photons actually are qubits, etc. But I will maybe jump to the next thing. The little thing. Is this the ultimate single photon interference experiment? Not quite. Because there was an idea by John Wheeler, which is, let's make an interferometer like that. I split the two beams and then I recombine them. And so if this beam splitter is there, the two beams recombine and I expect interferences. If the beam splitter is not there, so this photon will go straight, this photon will go straight, and then we will see the particle nature of the photons. So depending on the fact that this beam splitter is here or there, I can see the photon either as a wave or as a particle. But Wheeler's super nasty idea was to tell, let's first split the photon, and while the photon is flying in the interferometer, then I decide whether I will put or not this beam splitter. So decide to insert the output beam splitter or not, while the photon is already in flight in the interferometer. So this is called Wheeler's delayed choice experiment. So we did that, also with Alain and company. Okay, so this is a single photon source with the NV center. We split it, and then we send it in the interferometer. So you need some time to decide whether you will see the wave of the particle. So there is a little trick here with a switch, electro-optical switch, and you need a long interferometer because you must have time to decide randomly what you will do. So it was a 50 meters long interferometer, so this is the interferometer. These are the guys. And so this is just a 50 meters long pipe. It's a plastic pipe. It's not under vacuum. It's just for protect from wind, basically. There is not much wind. It was a basement of our building. But you see, at the end, there was the single photon source. And at the other end, there was a random choice. So again, it's a little bit like that. So you emit the photon, you split it. It travels 50 meters. And while it is traveling, there is a clock. And here, a fast random decision, which is done while the photon is traveling. And then you have two configurations. One configuration where the two photons go their way, and another configuration, closed one, where you basically interfere the two paths, and it's done very quickly and randomly. So what do you get? Well, you get what is expected. That is, when the path is closed, then you get fringes. So you see, the photon is a wave. And when it's not closed, you see independent clicks, anti-bunching. Then the photon is a particle. So, well, you cannot cheat. And so this is sort of, it's an illustration. So this article was published in Science. So we got a funny referee comment. Okay, it's a nice experiment. I will accept it for publication in Science. But don't do that too often. Okay, so maybe I make a little stop for questions here. Fast question if you want, because after that I will change subject. So if you have a... Yes, Vanderlei. Yeah. Yes. Somehow tell us that waves and particles, they have to survive together. One giving the amplitude, the interference probability. Yes. The other one giving us the particle, whatever is close. So you believe that this experiment is already proving that particle and waves, they are always together? So what I usually tell is a photon a particle or a wave? So the usual answer I give to students is it's neither a particle nor a wave. But it's very convenient for us, depending on the experimental setup, to consider a photon as a particle or as a wave. In some sense, as this was not told by Bohr, so the experimental setup decides for us. And so basically, given the experimental setup, you have to introduce the experimental setup. And the photon itself is a quantum entity. you see, this is my cautious answer. I would, because classically, wave and particles are incompatible. So you end up in a dead end. It was the initial problem. So the end of the dead end is some I will come back to that later, but it's to admit that the quantum entity is not a classical object. And so it's neither, actually, of the two. Yes? Yes, well, it's a little bit questionable, because if you do a Mach-Zehnder interferometer, for instance,
yeah, but you send one and you never send the second.
yes, you send only one. So if you send only one, and if you adjust your Mach-Zehnder interferometer, you can predict with certainty, for instance, that the photon will be detected here and never here. So you only send one photon, and for sure you can predict it will be detected here, and this happens. Yes, so it's sort of a, verification of the prediction of an interference effect at the single photon level. You buy it? No? Okay. But I agree also that when we do such experiments, obviously, in order to see these curves, we detect many, many photons. But what I just said is that if you go to this extreme, you see here, decided between this and that, one photon is enough. Okay, it can be discussed. So, we go on? Okay, so let's go on. More than one photon, two photons, obviously. And so, initially, you know about Einstein, he sort of proposed the idea of a photon, which works very well. But then he did not like quantum mechanics. And he proposed in 1935, it was 30 years later, this experiment with pairs of entangled particles, which was described in a very famous article in 1935, Einstein, Podolsky, and Rosen. So they propose a definition of reality, locality, and they conclude that the formalism is incomplete. So I will give more details. It means that it's like if quantum mechanics was hiding something from us. I will explain in more details later. So Niels Bohr disagreed. So they said quantum mechanics is not complete. Bohr answered that it is complete. There was a debate over many years, but actually not much attention for physicists, because quantum mechanics was so much successful that people used quantum mechanics and did not try to go into much details and blah, blah. So it was considered a little bit like a philosophical debate. But then came John Bell in 1964, and John Bell proposed a very strange thing, which is a mathematical way to check a philosophical idea. A philosophical idea about the nature of reality. So let's look at that. So here is John Bell. So the idea is to deal with entangled pair of photons. So we don't have now one photon, but two photons. So one photon goes on one side, the other photon goes on the other side. Then you can make what is called a polarization measurement. So you send your photon to a polarizer, and there are two outputs, parallel or deviated, let's say, that I call +1 or -1. Same thing on the other side. And I can rotate this polarizer. This orientation of polarizer A is adjustable. So now I'm interested in correlation. Correlation means that, for instance, for some orientation of the polarizer, if I get +1 here, I will get +1 here. And if I get minus, I will get minus. This is a correlation. So the idea is, how can we explain such correlation? So just think that your photons are twins. So if you know that these two guys are two twins and they both have blue eyes, you are not surprised. They have blue eyes because they have the same genes, the same parents. So the idea of Bell is try to do the same with the photons. So then he introduced what is called supplementary parameters, the lambda, common properties, like the gene of the twins. And so the result here will be +1 or -1. It will depend on the orientation A here, and on the lambda describing a given pair. Same thing on the other side, and you have a random distribution of the lambdas. It's like, twins. Some twins have brown eyes, some twins have not every twin has blue eyes, because there is a randomness in the genes, but the correlation is explained by the genes. So it's a very simple model. And then you can define what is called a correlation function. So you make, like in statistics, the average of the product of the two results A and B, which are both +1 and -1. So the average will be between 0, +1, and -1. And then Bell-Shone, it's a very simple calculation that you can build a quantity which is made from 4 different correlation functions with different angles. So you have two A and A prime on this side, B and B prime on this side. This creates this function. So these 4 numbers are all between +1 and -1. So you would expect this S to be between +4 and -4, because there are 4 quantities which are between +1 and -1. So all the trick is that Bell has shown that this quantity with the minus here, the minus is critical, is not between + and -4, it is between + and -2. And this is really surprising. Just this simple hypothesis about these so-called hidden variables or basically reduces the amount of correlation. So they cannot be all one together, for instance, but they are bounded this way. Now, if you take quantum mechanics, entangled pairs of photons, then you can calculate, because it's a measurement, you can measure it. Maximum value of this S parameter for this choice of angle, you see A prime on one side, B and B prime on the other side, and it reaches the value 2 square root of 2, which is clearly larger than 2. So it means that there is a conflict. That is, quantum mechanics does not agree with this simple, naive, hidden variable model. So it took some time to realize, so it was in 1964. Then there were people started to think about it. So first, the Bell's inequalities, the initial Bell's inequalities were not very easy to check experimentally. So there was a first work to make them sort of manageable for experiments. So you have to make little tricks. I can explain if you wish, but what I've seen here actually is this inequality, this CH-SH inequality. It's not original Bell's inequalities, which was a little bit more tricky. It is this experiment done by these guys in 1969, and you see a ball name here, which will come later again. So John Clauser actually did the experiment in 1972, and he found the violation of Bell's inequalities, that is quantum mechanics. But at the same time, there was an experiment done in Harvard. Usually in Harvard, they are rather good, but they found Bell's inequalities. So they disproved quantum mechanics. So it was a sort of a tie. Then it was done again. Clauser redid an experiment, found again quantum mechanics. So these experiments were very difficult to do because the number of photons was very small. It took super long to integrate. And it was a little bit unclear at the end of the 70s what the situation was. So this is when Alain Aspect started the experiment, so et al. So I'm one of the et al. So he designed, I will give more details, the source of entangled photons, then a much better improved scheme, and also the idea that, I will give more details on that also, to check directly quantum non-locality by implementing a relativistic separation. It's a little bit like Wheeler's, you remember. You first send the photon, and then only later on you decide the measurement to be performed. So this is where I started as a student in 1980. So this was our experiment in Orsay. So the idea was to excite calcium atoms to the upper level of an atomic cascade, and with angular momenta 0, 0, which meant that these 2 emitted photons were emitted precisely in the entangled state we wanted to measure. So we used lasers. So you see, this is a vacuum chamber, old style. There was an atomic beam, not called atom at the time, just an atomic beam of sodium, which was excited by a dye laser. So this is a rhodamine 6G, nobody knows that anymore. This dye laser, plus another laser, this one, which was a krypton ion laser. And so we got a very efficient excitation of this thing. So many of these pairs were emitted, contrary to Clauser's experiment. And we could check the experiment. So we did 3 experiments. The first one with like Clauser, the first one with improved polarizers, and the last one with the switches. I will tell more. So this is the very first one experiment we did. So it's same thing. So there were not yet multi-dielectric polarizers. So the polarizer was a really strange thing. It was a succession of 10 Brewster plates, and the polarization in the plane of the screen goes straight, while the other one is lost somewhere. So it was a polarizer about that big. It is in a museum now. It was fun to rotate. But it was similar to the experiment Clauser 72, and we found a violation of Bell's inequalities. Then Alain got another idea. Who is that? Well, that's me, some years ago. And Alain, so we discussed a lot, so you see a lot of coffee is there needed to make Bell test. And then the idea of Alain was to replace this big polarizer by polarizer cubes. So he went to Amsterdam, he went with a big bag throughout the frontier. You know, in the 70s, going to Amsterdam with a big bag was a little bit suspect. But okay, he brought back these polarizer cubes, which are sort of modern polarizers and much more compact than the old pile of plates. So then we did this experiment. Now we had really two outputs, +1 and -1 on each side. So the real stuff was like that. It was a big machine, you know. The cube was inside with big photomultipliers here and there, and everything was rotating. It was like 30 kilograms. There are, you know, ropes and wings so that we could rotate that. Anyway, we did the experiment again and again. Very good agreement with quantum mechanics and violation of Bell's inequalities by 40 deviations, even more than before. So finally, the real aspect experiment was to introduce this switch, that is to have a way to check locality hypothesis, which is in Bell's theorem. You have to assume that the result here does not, on this side A, does not depend on B. You don't want B here. Similarly, here you don't want A in the way you detect what you detect here. And also you don't want any effect of A and B, the orientation of the polarizer, on the way you emit the sources. And in order to check that, you use relativity. You just say, if I decide A between A and A prime and B and B prime after the photon have left the source in a very fast way, then, okay, I can check that this red line are really there. So there is no way to move you have seen the polarizer, like 30 kilograms, no way to move it in a few nanoseconds, which is the flight times of one photon to the other side. But Alain's idea was to make a switch, that is a common switch, which is able to send the light either here or here very quickly in a time faster than the transit time of the light, which was about 20 nanoseconds. A little bit more detail. So the switch is, this is a switch. So it's a water tank. It's water, actually. You make a standing wave in water. And so this standing wave in water is something like that. When the standing wave is 0, there is no, it's just water, so it goes straight. And when the standing wave is on, there is a diffraction grating, and then the light is deflected. And so it switches very fast between straight and here, and you go to two different polarizers in different directions. So the switching time was about 20 nanoseconds. The transit time of the light was about 40 nanoseconds. So we are sort of right to make a real check of this relativistic, full relativistic separation. So this was done in 82. So it was more difficult, reduce signal, several hours, so instead of minutes, switching not fully random, but clearly Bell's inequalities were violated by 6 standard deviations. So each measurement were space-like separated, now, etc., Einstein causality and force, etc. So as I said, so it was the first test of quantum locality, non-locality in that sense, with a fast switch, which was done by Alain. Then it was 82, 40 years ago already. So there were many more experiments because there were some loopholes. We were missing a lot of pairs. It would be nice when you do such experiment to detect all pairs. But in this old experiment, we detect about fraction 10 to the -3, one photon over 1,000. So it was not super good. So people try to improve that, to detect more photons, also to have a larger distance, fully random switching, etc. So you see the third bold names, which is Heiliger. We contributed to that. And then after a lot of many efforts, it was possible to close all loopholes, that is, to make an experiment which fulfills all the criteria which are requested by the theory. So this was done in Vienna. So Vienna is Zeilinger Group. So if you know Vienna, this is a Hofburg, Imperial Palace. And at the bottom of the Hofburg, there is a bunker in case of nuclear war or whatever. Anyway, it's a long corridor, and then you can have long distance to propagate your photons. So this was a source, and then again the polarizer, random choice, but much larger distance, so much better random choice. Also, all photons were detected because the photon direction were directive. It's no more atomic cascade, it was parametric fluorescence. So this was done in 2015, super agreement with quantum mechanics again. A similar experiment was done in Boulder, Colorado, at NIST. It's very similar setup, actually, and also very similar result. And the third experiment was done in Delft. So this one is interesting because the entangled things are no more photons, they are spins. So it's NV centers, actually. You know about NV centers. So you can entangle remotely the spin of NV center by using what is called entanglement swapping. So first you entangle your spin with a photon on each side. The photon propagates. Here you make a so-called Bell measurement. And once, if the result is good, it prepares the two spin in entangled state. And then you can make the not polarization measurement, now spin measurement on the two spins, and again, check Bell's inequalities with very high efficiency. So all three experiments, now loophole free, all hypotheses are satisfied, agreed with quantum mechanics, and violated Bell's inequalities. So this is a paper by Alain in 1915. You see with all the experiments. There is another one in 17, actually. So you see, by closing two loopholes at once, three experiments at Delft, three experimental tests of Bell's inequalities removed the last doubts that we should renounce local realism. So the Bell's hypotheses are usually summarized as local realism. So they also open the way to quantum technologies. So in some sense, these experiments both close the old history, because now the experiments are as good as we can do them, and also open new direction by telling, okay, now entanglement is really some stuff which is there, and that we can to exploit. And you know the consequence of that. Yes, so this is you see, the names in bold were not in bold by chance. I think these people really deserve it. That is, Clauser is really, when he started his experiment, he was in complete darkness. He was really a pioneer. Nobody understood what he was doing. Then Alain introduced all this relativistic argument, and then Anton Zeilinger just completed and did the ultimate experiment. So I think over 50 years now, it sort of closes the story. Okay, little stop for questions. Where I am with time, by the way. Yes? Fine? Are there questions? You all know that.
You know, we see that the generations of experiments is trying to increasing the arms, so there was no question, and there was time to flip things, to have no doubt about what you're measuring, right?
That is, the simple reason to increase the length of the arm is to have time to make a full random switching. Because if you want to make a full random switching, you need to make the choice. So you have a quantum random choice generator. And also to switch. It's a little bit like the Wheeler's experiment. You have seen our experiment was 50 meters long, just to be able to make efficient random sort. So you see these experiments are also about 100 meters long, which is a typical time you need to make a proper completely random switching.
I have one, like a curiosity. You constructed your own acousto-optical modulator using a tank of water. Is that right?
Yes.
And how efficient was that?
It was super efficient. No, I show that. This is why it was done this way. You see, I don't. No, the efficiency, which is, but basically it was losing no light. So you see, the efficiency, that is, all light was there, but here the extinction was not perfect on this side, and it was not perfect on the other side. So yeah, it was efficient, but with imperfect extinction.
Because in water, ultrasound can cause cavitation and all the kind of perturbation, but that was not limitation.
You say, sorry, that's...
Ultrasound
Yes,
in water
yes.
can cause cavitation,
Ah, yes.
little bubbles that explode
yes.
and things.
No, it was very carefully adjusted. So
Okay.
it said the power of microwave was carefully adjusted. It took a long time to adjust. And yes, you had to avoid cavitation, otherwise it would be a mess. Now, this was characterized very carefully by Jean Dalibard, who is a super good experimentalist. It agreed well with theory, etc. But now you see, the big problem is that we had big beams. Now with the new experiments, they are very small beams because it's parametric fluorescence. So it's basically coherent like laser beam. So if you have a laser beam, it's much easier to switch quickly. But for big beam that size, it's not so easy to make a fast switch. So this was the trick was, first Alain tried with crystal. But with crystal, when they were putting the microwave on the crystal were breaking. So he was sort of desperate at some point. He told me, my experiment will never work because I will never get a switch big enough. And then he looked at many books and he found that water is a super good acousto-optic medium. So so there are still the transducers. So you see the transducers are here and there. But instead of being stuck on a crystal and breaking, they are just in water. And water never breaks. No, that's a good trick. You need some imagination. Yes, so yeah, one shouldn't tell that. Yes, actually, this was not the initial idea. The initial idea was just to have a big piece of glass, but it was breaking. So, which means that the power was maybe not so small, but water could make it. Okay. So let's go on. So after that, what happens then? Okay, quantum technologies and other stuff. So as I told at the beginning, we know this first quantum revolution, which is quantum mechanics explains the structure, interaction, etc. So we got lasers, microelectronics, etc. And this name of second quantum revolution, which was actually introduced by Alain, I think, is that when reaching the level of individual quantum object, you have surprising properties, basically superposition, which is interference, and entanglement, which is Bell's inequality evaluation. And these quantum properties open the way to new ways to process information, which is called now quantum information. So basic ideas are, for instance, sources of individual photons. So I show you these NV center sources. This one was done in another lab. It's a solid state. It's a microcavity with quantum dots inside, which is also able to emit single photons. You can also get quantum bits, a superposition of 0 and 1s, which are just an extension, in some sense, of interference effects. And then you can do plenty of things. You can do super sensors, single atom sensors, micromagnetometers, super clocks also. You can do quantum simulation. So these are these arrays of traps that we have developed in our labs. So you can trap single atoms in a tiny dipole trap and make any shape you want, and then program interaction between the atoms. And it's working really nicely. There is a company now selling that. You can buy it. This was done by Jean Dalibard. It's a vortice sort of simulation also. So this is without a BEC, and this is with a BEC. Another application is quantum communication, quantum cryptography, most less. So trying to use this quantum stuff to do super secure communication. So presently, I'm working on that. Again, we published in Nature in 2003, another one, which has been going on also, and I'm actually still working on that. It's a special version of quantum cryptography, which is called continuous variable quantum cryptography, where we don't use clicks, but we use coherent detection, homodyne, heterodyne detection. It's very close to current telecommunication, actually, because current telecommunication, very high speed, actually coherent telecommunication. You use local oscillators. And you just tweak a little bit commercial devices, and you end up in a quantum cryptography device. So this is what we are trying to do with some companies, Nokia, for instance. And the last one, super famous, is quantum computing. So trying to make a new, to increase algorithmic power, again, by using quantum bits. So all these things are very active, okay, so, but there will be maybe as many talk as lines on the slide, so I will sort of skip it. I will speak a little bit about something else, which is, okay, let's go to that, come back to that. Oops, sorry. What you get from that is that, as a conclusion, is that Bell's hypotheses are wrong, since they are contradicted. The Bell's hypothesis imply Bell's inequalities. Bell's inequalities contradict experiments, so there is something wrong in Bell's hypothesis. But what is wrong in Bell's hypothesis? And this is a sort of a tricky issue. So the best thing is to ask Bell himself, because Bell explained, he was a very smart guy, he explained what would happen if he would be wrong. So let us anticipate that quantum mechanics, this is from Bell, this is from this book. Let us anticipate that quantum mechanics works also for Aspect. It did not work only for Aspect, it worked for many others. I will list 4 of the attitudes that could be adopted. First, the efficiency of the counter and so on are essential. Quantum mechanics will fail in sufficiently critical experiment. So this is dead. This was the whole issue of Loophole-free Bell test, which was to get rid of this thing. So now the experiments are so good that you cannot invoke that argument anymore. Let's go to the next. There are influences going faster than light, because anything small within relativity should be constrained. So now, if you admit something going faster than light, then you can violate Bell's inequalities. Okay, you cannot send messages faster than light, but actually, and even show Nicolas Chaz that it's not only faster than light. Actually, if you want to violate Bell's inequality, it must be instantaneous. But still, it will not violate relativity, do some little trick. I will explain that later. But this is a possible option. The third option is when you make your choice, you make random choice. But actually, there is no random choice in nature. Everything was decided at the Big Bang by God or whoever else. And then, okay, so there is no free choice. So A and B are not independently variable. Einstein causality can survive, but separate parts of the world become deeply entangled, and the apparent free will is entangled with them. So Alain or I agree with this is completely crazy. That is, if this is true, it's called superdeterminism. There is no choice nowhere in nature. Everything has been, but it's so crazy that I don't really know how to manipulate that. But I will also come back to that. And the fourth one is the whole analysis can be ignored. The lesson of quantum mechanics is not to look behind the prediction of the formalism as a correlation. Well, that's quantum mechanics. So it's a famous shut up and calculate position. Well, so I like none of these. So I've been doing some philosophy to try to understand. So it will be another talk. This is a talk I gave in Cordoba. I will just try to develop a little bit. So let's assume there are influences going faster than light. Let's admit that. Then you violate locality at the hidden variable level, which means that if you would know the hidden variable, then you would violate the locality, but you cannot know them, and so everything is fine. It's a little bit involved, but still, if you like it, you can. Sorry, oops, what did I do there? Yes, if you like it, you can keep it, and so this is what is done by Bohmian, for instance. Bohmian thinks that there are hidden variables, but they have to be non-local. So this creates a strong tension with relativistic causality, and honestly, I don't like it very much. Yes, so this is a superdeterminism, the violation of Kirchhoff. There are no random independent events. So full predetermination, no actual randomness. Again, I don't know whether you like it, but I don't. Okay, but some people like it. That is, for instance, Gerhard Tuff is a Nobel Prize winner. And he thinks that everything has been sort of pre-programmed at the Planck level at the origin of the universe. Well, okay. So, next one. The whole analysis can be ignored. This is not really a physicist position. But violation, there is a way to violate Bell's inequalities by violating what I call predictive completeness, which is it's an old term which was introduced by a guy named Jarrett, which is the idea that if you know psi, you don't know everything. So psi is incomplete. But this is just what Einstein was telling. And so we are back to the initial step. No, you will see. But still, let's admit that psi is incomplete. Then you need something more, and then this is a possible way. So this is detailed in the all the equations are in this paper. You can see that you can violate Bell's inequalities in this way. So here you need randomness for this to work. You need also contextuality. And actually, the trick is you conclude from that psi is incomplete, just like Einstein was telling. But Bohr was saying, oh, but no, but psi is complete. But you must specify the very condition that allows you to make predictions in the future, which is a strange answer. But actually, what does that mean? It means, for me at least, that psi has to be completed indeed, but by specifying the measurement apparatus. So if you say that psi is not complete, because if you just have psi, you don't have a full set of mutually exclusive results. In order to have a full set of mutually exclusive results, you need to specify what you want to measure. So, okay, I'm going fast, but this idea can be developed. That is completing psi from above. The idea is that you don't complete psi from below, but you complete psi from above. By specifying the measurement context, it seems to be a valid option. But is it compatible with physical realism? Because all the stuff was, remember, it was realism. So yes, my claim is yes, but not everybody agrees, I must say. So what about realism? So first, what is realism? So I give a simple definition of physical realism. The purpose of physics is to study entities of the natural world existing independently from any particular observer's perception and obeying universal and intelligible rules. So this is realism. No? Well, I don't know. For me, it's realism. This means that, okay, I'm thinking, but this is a bottle for me and for you and for everybody around, and we will agree on the fact that it's a bottle, and we can understand what is a bottle. This is a naive idea. And this applies to quantum mechanics, actually. So what I claim with our colleagues on this these co-authors of this philosophical paper, we can keep physical realism in this sense, free choice, elementary and global locality, but then the description given by psi is predictively incomplete. How to complete psi? Not from below, because hidden variables don't exist unless they are non-local, and you don't want that, but from above in order to get a full probability law over a set of mutually exclusive results. Okay, well, so it's a possible way. So it's many people speak about that because it's related to what is called contextuality. Contextuality is a way to look at quantum mechanics. So it's sort of, you may, so I'm going very fast because it would be a full talk, but you can see presently that it's a little bit shaky. The most widespread idea is that Bell's inequalities violations are due to non-locality, but actually you can shift that a little bit and tell that it may be due to contextuality, but it's very controversial. And so in Cordoba, where I was a few days ago, people are strongly arguing along this idea. Yes, the initial motivation of all this stuff was sort of philosophical. What does quantum mechanics tell us about the nature of reality? So, okay, so some people, including me, are still thinking about that. It's very far, well, it's rather far from quantum technologies, but I think maybe two directions are interesting. Okay, just to finish, so this is the team which did the Wheeler's experiment with Jean-François, etc. And with, behind that, Alain and me, so we didn't really do the experiment. So I said, Alain Aspect, we are the godfathers. But now you can also look at that a little bit like a family. Okay, so Alain is a father. I'm the first PhD of Alain, so I'm sort of the son. And my first PhD is Jean-François Roch here, the grandson. And Vincent is the first PhD of Jean-François, so he's a grandson. And now Vincent has PhDs, which are grandson. And so Alain is actually a grandfather, 5 generations of scientists. Okay, thank you and bravo, Alain.
Thank you very much, Professor. Now we have time for questions. Pablo?
Thank you for the talk. I have a question that I'm not even sure how to formulate it, because you thought that this contextuality of quantum mechanics and things like
Sorry,
this.
I don't hear you very well. Maybe can you remove the mask? Time just.
So I have a question that I'm not sure how to formulate it. So you talk about this contextuality in quantum mechanics, and of course I understand that a lot of this is like philosophy, but what this means like in my experiment to say that quantum mechanics is contextual or non-contextual and things like this?
So yes, it's a widely developed subject. So now you can find in the literature contextuality inequalities. That is, there are inequalities that you can measure also on experiment, which tells you that you are contextual in a quantum sense. The most known example also is Cohen-Speker's theorem. So I have a full talk on that, but I don't think it's much time to present it now. But Cohen-Speker's theorem, it's a simple illustration of a contradiction, which is that if you take different measurements by different apparatus in quantum mechanics and can to decide for an ensemble of measurements that they are all true or false, this doesn't work. This is impossible. So basically, in different measurement contexts, you have to redefine a new probability law, and this new probability law between the different contexts are not connected classically. So it's another way to see contextuality. It's the fact that, very naively said, if you have a set of non-commuting operator observables, you cannot give value to, cannot decide that all values are true or wrong, because some of them have to be described probabilistically. And so, yes, so there are many ideas, but it was just sort of a sketch. Recently, there was a review paper on contextuality by Adam Cabello and company. It's an archive. I think he's missing some points, so I have added a comment to his paper. Yes, okay. So you see, this is a sort of active subject because there are a lot of ideas and not much agreement yet. So I don't know whether an agreement will emerge at some point or not. So it makes very lively conferences.
Thank you.
Thank you. More questions? Dalila?
Thank you for the talk, Philip. So why psi needs to be something that has all the information?
It's a view on psi. That is, there is no real reason, but people do think that psi contains all the information. The most extreme way is Everettian, many world theory. They say that there is only psi. And when you do a measurement, for instance, you don't get different results, but it's a branching of psi. And so you have a universal wave function, and everything is within this universal wave function. It contradicts what I said. But just to give an example of people who are really convinced that the ultimate reality is nothing but psi. No, they write many papers. They are not completely nuts. But you see, it's why what people call ontology of psi is still debated since the beginning. Is psi a real wave? So in our approach, for instance, psi is just a mathematical tool in order to calculate probabilities. And so if you say that, okay, then it's all in your mind. So you are sort of, super non-realistic because everything is in the head of the agent, etc. No, I don't say that. I say we have objects. Objects have properties. And in order to manage this object and properties when they are quantum objects, I must use psi to calculate probability, well, just like I use Gauss law or Poisson law for classical probabilities. So it's a different kind of probabilities, but and the different behavior of the object because they are quantized and contextual. So you have to, this is the title of you have to change your view of realism. Classical realism is the idea that you attribute properties to objects, and then from this object and properties, you build everything. Like you build the house from the stone. In quantum mechanics, it does not work because if the stones are entangled, you end up in a mess. So you cannot really build a house from the stone because there are probability. If you just have a bell pair, for instance, the entangled set is completely defined. Entropy 0, you have a perfect definition of your global state, entangled state. Now, if you look one of them, it's perfectly random. It's completely bizarre. So it means that you know completely the whole and completely ignore the part. In classical physics, this never happens. If you know the whole, if you know the house, you also know, you can at least determine the position of all the bricks. And they have well-defined position. In an simple entangled state, you know perfectly the whole state, but you ignore absolutely everything about a single photon. The measurements on each side are completely random, but they are correlated. So you see, you have to change a little bit. This is our argument. You have to redefine a reality which is still a reality. The point is that people say, if you redefine the reality this way, it's no more the reality. Well, so, voilà.
Thank you, Danilo. More questions? Don't be shy. Okay.
The last part of your talk, it seems that we still have a lot of questions to ask to quantum mechanics in general.
Yes, sure, I think so. Well, there are, and this is just a low energy everyday quantum mechanics. Obviously, some people connect that also to quantum gravity and to big issues like that, which are really completely unsolved, yes.
Now, my real question is, what kind of experiment can you visualize that will solve some of those questions?
So Bell's test was one experiment who did that to some extent. It was, as I said, it's really unusual to be able to test sort of philosophical ideas on the nature of reality, to turn them into mathematics and to turn them into experiments. So for instance, with all these things that I have shown here, all these options, presently, there is no experiment which is able, yes, so you see, for instance, these options, 3 options, it doesn't look so crazy, but there is no difference in experimental prediction. So people are thinking, obviously, if we were able to find a difference in experimental prediction, it would be a big step forward. But so now, to be avoided, it just means actually I don't like it. But people who are convinced that they are right, I cannot prove them wrong because there is no experimental test which would prove them wrong. I can just tell it corresponds to a vision of the world that I don't like. It's an ontology. So we worked with a philosopher. So an ontology means defining what is. It's a science of being in philosophy. And so the basic rule in philosophy is that you cannot demonstrate ontologies. If I think the world is this, and if you tell me no, it's that, typically at the elementary level, we cannot tell. So there is an arbitrariness. So here we are stuck to this thing. So these views of the world are completely different. So they sound contradictory, but there is no experimental way to, or if you find one, it's a big deal. Please tell me.
Okay. No more questions? Oh, if not, I would like to congratulate you again, Professor Philippe. Okay, Professor will stay here in this afternoon, and also the people want to meet with us to see the match. You'll be invited, everybody. Thank you.